Today we are building off our application of sine, cosine, tangent to triangles, and we're kind of taking a break from sine, cosine, tangent today to talk about the Pythagorean Theorem. So this is another day where you have kind of covered this already in geometry, and we're pulling it back in. So let's start off by taking some notes here. There's a note section on your worksheet titled Pythagorean Theorem. It kind of mentions what it's for. The Pythagorean Theorem can be used to find a missing side for right triangles. And let's go ahead and get down this formula. Put that in the box on the left. A squared plus b squared equals c squared. And it really doesn't matter where a and b are. Make sure to get this sketch in your notes as well. Doesn't matter where a and b are as long as c is the hypotenuse. So let's see how this plays out in an example. We have 4, we have 3, and we have a blank hypotenuse side over here. So first thing I want to do, if we're going to find the missing side length, is I'm going to label everything. We know that C has to be the hypotenuse. That's going to be our unknown. That's what we're solving for. And we can choose A to be equal to 4 and B to be equal to 3. It wouldn't matter if we had switched those around, however. So we're going to set up our formula. A squared plus b squared equals c squared. So in this case, it's 4 squared plus 3 squared equals c squared. And I know the way your notes are, make sure you jot down this triangle sketch, and then you can work below the triangle with the work that I'm doing to the right here. So 4 squared is going to give us 16. And 3 squared will give us 9, and we'll just leave that as c squared on the right. And 16 plus 9 gives me 25. So 25 equals c squared. And so if 25 equals c squared, then c is going to be the square root of 25. And we can either punch that into our calculator, or we know what that's true to be, and that means that 5 is equal to c. So let's continue trying this on another example, and these next two we're going to continue solving for c here. So we have 2 on one side, 10 on the other side, and it looks like our hypotenuse again is the unknown. So let's make sure we label it. With c over there, I'm going to set a as 2 and b as 10. And go ahead and pause your screen, try this yourself, and check back when you're done. If you get a decimal, please round it to one spot. All right, so my setup, I'm going to have 2 squared plus 10 squared equals c squared. And that 2 will give me 4. That 10 squared will give me 100. That's equal to c squared. So then we get 104 equals c squared, which means that that square root of 104 is equal to c. In that case, I'll punch that into my calculator, the square root of 104. That's going to be 10.2 if we round it to one decimal place. All right, and let's do one more example where we're dealing with a missing hypotenuse. Again, pause your screen, try this yourself, check it against mine. C is going to be our missing side. A is equal to 5. B is equal to 12. We set up our formula, so we'll have 5 squared plus 12 squared equals c squared. This becomes 25 plus 144 equals c squared. And in that case, it is 169 equals c squared. And if we take the square root of 169, that will give us what c is equal to. And in that case, it is 13. Okay, let's do a few more of these just to get good practice. But in these cases, we have the value for c already. You'll notice that in example 4 here, our hypotenuse is this side length of 13. So we're going to need to solve for something else, either a or b. So let's make our missing side length a. Let's solve for a here, and let's set b equal to 12. So if we set this up, we have a squared plus 12 squared equals 13 squared. So we can simplify that. We have a squared plus 144 equals 169. And here's where we need to make a modification. All right, we want to get a all by itself, and 144 is being added to each side. So we need to subtract 144 from both sides. And that'll leave us with a squared equals 25. And then again, we can get rid of that square sign by taking the square root. So a is equal to the square root of 25, which in this case means that a is equal to 5. Let's do that on two more examples. Again, feel free to pause your screen as you go here. Make sure to be rewriting all these triangles so you have them as reference, looking back. So in this case, our hypotenuse is 9, so C is equal to 9. Let's make our missing side length A, and set that top side length to B. Then we set up our formula, a squared plus 4 squared equals 9 squared. We can start simplifying that formula, a squared plus 16 equals 81. We can subtract 16 from both sides and leave us with a squared equals, let me check that out, 81 minus 16 is equal to 65. And so that means that a is going to be equal to the square root of 65, meaning that a is going to be equal to 8.1 if we round to one decimal spot. All right, last one here. Again, hypotenuse is going to be 10. Let's set our missing side to A and set 6 as our B. Set up a formula, a squared plus 6 squared equals 10 squared. Okay, that'll give us a squared plus 36 equals 100. And if we subtract 36 from both sides, we can rewrite that formula one last time. That'll be a squared equals, what is 100 minus 36? It looks like it is 64. And so if a squared equals 64, then a is going to be equal to the square root of 64, meaning that a is going to be equal to 8. All right, so there's one more section of notes, and this kind of ties it back to our unit circle. So make sure we get this formula down here. Basically, when applied to the unit circle, the Pythagorean theorem can be written as sine squared plus cosine squared equals 1. And if we remember what our unit circle looks like, this image on the right, which you do not need to copy down, we have a radius of 1. That's always our hypotenuse. Cosine is our width of our triangle. Sine is our height of our triangle. So if we were to apply the Pythagorean theorem there, we could label C as that 1. Cosine could be our B, and sine could be our A. And you would see that all of that could feed into this formula here, because 1 squared is simply equal to 1. So let's quickly see how that can be applied for us. Basically, if we know what sine is, we can easily find out what cosine is, applying that Pythagorean theorem. So in example 7, if sine is equal to 0.5, then we can find out what cosine is. So we know that sine squared plus cosine squared is equal to 1, regardless of what angle it's at. And so we know that sine squared is 0.5, so 0.5 squared plus cosine squared is equal to 1. We can find that 0.5 times 0.5 is, this would be 0.25 plus cosine squared is equal to 1. And we can subtract that from both sides, that 0.25. to get cosine alone. And so that means that our cosine squared is equal to 0.75. And that means that cosine is equal to the square root of 0.75, which in this case, if we take 0.75, find the square root of it, is going to be 0.87 if we're rounding to 2 decimal spots. All right, let's try this on one more example. This time we know what cosine is, so let's find sine. So cosine is equal to 0.71. Let's write our Pythagorean theorem. Sine squared is our unknown, so sine squared plus 0.71 squared equals 1. So sine squared we can leave as is for now. That'll be plus, looks like 0.71. If I square that, I get 0.50. So plus 0.5041. That's equal to 1. So let's subtract this from both sides. Minus 0.5041 minus 0.5041. That cancels out on the left, so we're just left with our sine squared. And on the right, 1 minus 0.5041 is going to give us 0.4959. And if we take the square root of that, that'll give us what sine is equal to. So sine is equal to the square root of 0.4959, which means that sine is equal to 0.70.